Yes, yeah, I'll just briefly take 1 minute to introduce you. Good afternoon. So I'll happy to introduce Dr. Mukul Bhattacharya. Mukul actually basically working as a postdoctoral, Eberly postdoctoral fellow at University, Penn State University, and he's basically working on the theoretical modeling several neutrons, magnetized stars using predicting previous laboratory experiment or what LIGO can detect everything, details, nucleosynthesis element. So this is his the mainly today's talk. Other than this, he also works in the several area like modeling in the gamma ray blast, white dwarfs. Also, he work. Yes, so these are the wide interest on the theoretical astrophysics, and basically he did his masters from the University of Texas, Austin, UT Austin, and before that he did basically 4 years earlier UG physics from the ISC Bangalore, from where he moved directly to the for PhD degree, and he here worked also sometimes here, came here for a short time, short project, working in the condensed matter physics during UG time. So slowly he's diverted interest on the astrophysics. So now he's strongly working on the astrophysics. So you'll hear from the Mukul. Yes. Thank you.
Thank you so much.
Thank you.
So let me know if all of you can hear me properly. Before I start off, I would like to thank my collaborators. So my postdoc is in collaboration between Penn State and Virginia Tech. My advisor right now is Kota Murase. Most of this work has been done with Kota's PhD student at Penn State, Jose Carpio. Before that, I was at Virginia Tech for 1 year. So I worked with Shunsaku Horiochi, who's a professor there, and his graduate student, Nick Ekando. So as he mentioned, I will be talking about nucleosynthesis in magnetized outflows, mostly from core collapse events, but I'll also go over mergers, binary mergers. So here's a brief outline of my talk. I'll be talking about what's the origin of light, intermediate, and heavy nuclei in our universe. I'll be comparing the nucleosynthesis yields in each of the astrophysical events. And by that, I mean core collapse supernova, CCSN, binary neutron star merger, BNS, and black hole neutron star merger. So we would focus on neutrino-driven winds from protomagnetars, which is primarily this, CCSNE. So CCSNE means protomagnetars. And then we have used a code which is called Skynet, and that helps us generate or simulate the nuclei abundance patterns in stars. And we want to test our results against the solar abundance or the abundance pattern that we see from other stars. In the middle, we also looked at whether the heavy nuclei which are created in these outflows can accelerate, and also if they can survive within these outflows, because only if they survive, we can see them on Earth. And then lastly, the third component of my work has been to look at propagation of these magnetized outflows within the progenitors. And it turns out that most of these progenitors are also GRB progenitors. So it's very interesting. We see heavy nuclei, which can be cosmic rays. These are also GRB progenitors, and there can also be neutrinos. So the last part is high energy neutrino emission. I'll try to wrap everything up and show how this can be used as a multi-messenger science on the same astrophysical object. So a brief background, we will look at this periodic table again later in this talk. So what this is showing is all the lighter nuclei. Lighter nuclei is mostly hydrogen and helium here. And anything from lithium to iron is considered intermediate mass nuclei. And anything that is heavier than iron is heavy nuclei, is what I will call heavy nuclei. And this periodic table is actually showing the rate or the abundance from 5 different kind of events. One is Big Bang nucleosynthesis, then there's AGB stars, then core collapse in blue, type 1a supernova in red, and neutron star merger in purple. So if you see most of this is black, like for hydrogen, means most of the hydrogen has been generated from Big Bang nucleosynthesis. If you see most of this being blue, then it means it has been generated by core collapse supernova and not Big Bang nucleosynthesis. So the x-axis here is the time axis. You can see this is 0 and this is 13.8 billion years, which is the current age of the universe. So the abundance on the left is the abundance of the nuclei at the start of our universe when the Big Bang happened. So this is the abundance of cesium at time t equals 0, and this is at time t equals 13.8 billion years. This is showing how different all of these 5 different processes, what fraction they have contributed here to the cesium abundance. So we see more green and more red means most of cesium has come from AGB or core collapse. A very small part has come from type 1a supernova. Our goal is to actually modify this periodic table. We want to add 2 more processes. To core collapse supernova, we want to add magnetized core collapse supernova, and with neutron star mergers, we want to add neutron star black hole mergers, and see if there are 7 instead of 5 events. How is this periodic table modified? So I'll come to that later in this talk again, once more. So again, going back to light nuclei, hydrogen and helium primarily, we know that they have been formed in the Big Bang nucleosynthesis. So the Big Bang picture is something like this. Uh, Big Bang happened here, and then the universe started evolving towards the right, 13.8 billion years. So uh, at the start of the universe, right after the Big Bang, uh, the electron fraction, which is Ye here, the equilibrium value for that was close to 0.5. Ye means the fraction of electrons that is there in the medium. So if this is zero point 0.5, then that means half of the nuclei, half of the particles are electrons, half of the particles are neutrons. So Ye is zero point 0.5 means Yn, which is mass fraction in neutrons, is also zero point 0.5. And because the medium is neutral, Yp, which is the mass fraction in protons, is also equal to 0.5. It started from everything being equal, the number of electrons, protons, and neutrons. But then as the temperature started dropping, because the protons are slightly lighter compared to neutrons, more protons started forming. Neutrons started decaying into protons, and the final electron fraction was larger than zero point 0.5. It became 7, 8 because proton number is decreasing, neutron number is increasing. So on. Sorry, the proton number is increasing because they are lighter. Because the proton number is same as the electron number, Ye has to increase from 0.5 and goes to 7 over 8. So at the end of this evolution, we get about 75% hydrogen, 25% helium, but we do not get lithium or heavier nuclei than that. So how do they come? How do they form? So we have to look at intermediate nuclei, lithium till iron, and their origin is in stellar fusion. So most of these intermediate nuclei are formed in the cores of stars similar to our sun, and these stars can fuse nuclei up to iron because iron is the most stable nuclei. So once it moves up to iron, we cannot really go beyond it because we have reached the most stable nuclei. And once these nuclei are formed within the stars, there can be events such as stellar flares or pulsations or supernova, which helps the star explode, and the matter from the star is then ejected into the universe. So imagine there was a star maybe 100 million years ago, which underwent a supernova, and the ejecta from that reached Earth. And that's how we have gold or platinum or iron here. We wouldn't see them otherwise. Uh, Now I'm moving to the heavy nuclei. So iron or heavier than that, there are predominantly 2 processes which are responsible for formation of heavy nuclei. One is called S process, the other is called R process. S, as the name suggests, is slow process. It's a neutron capture process. Both of these are neutron capture processes. So what happens is there is a seed nuclei. It can either be carbon, oxygen, iron. So a neutron is captured by that seed nuclei, and then iron becomes cobalt. That captures a neutron, and that becomes nickel. And then plus neutron, another heavier element. So it just shifts like that. This is a slow process because one, this happens around the AGB stage of stars, so around this part. So there isn't much time for S process to happen because it has to wait until the stellar revolution reaches this point. And also, there are not as many free neutrons in this part of the stellar revolution. There are less free neutrons, and some of these free neutrons, whatever is formed, decay back into lighter nuclei. So they are not stable, they're unstable. So these unstable nuclei decay back into lighter nuclei. They are not iron anymore, maybe they decay into carbon, oxygen, helium. So we do not get as much abundance in heavy nuclei as we see in the current universe from this process. So S process cannot explain our abundance. So there is something missing. The other half explains it, whatever is missing. It's called R process. It's called rapid neutron capture process. And the seed nuclei are captured, the neutrons are captured to the seed nuclei much faster in this process. Before the decay happens, there is more and more capture, and that's how you can get far more heavier nuclei than you can get from S process. So for comparison, here there is 100 neutron capture events which can happen per second, whereas in our process, you barely have about 1 per 100 to 1000 years. So it's much smaller. And this animation is showing you from time t equals zero point 0.5 seconds, which is the start of our simulation, as we evolve our code until about 100 seconds, how is the nuclei abundance changing? So the x-axis is number of neutrons, and the y-axis is number of protons. So for example, for iron, it's 2630. So it would be 1 point here. What is happening is first nucleosynthesis happens, nuclei are formed, they are going towards right and bottom, and then they are decaying back to this solid black line. So this solid black line is where most of the stable nuclei are. So initially there are nuclei which are getting formed here, but eventually they are decaying back to this black line, and that is what we are seeing in the periodic table. We are seeing everything that happens after the decay because these nuclei are very short-lived, maybe milliseconds, second order. So as you see here, zero point 0.5 seconds to 100 seconds. Just within that, they are all decaying to the stable line. So we, of course, have to compare our results with observations. And what observations do we have? The easiest one is to look at the sun. So this is solar abundance, mass number, and abundance on the y-axis. So this tells us for a given mass number, what is the mass fraction of that nuclei? And if you look closely, you will see that there are clearly three distinct peaks. One here around 80 to 90 mass number, the other here around 120 to 130, the other around 190. So these are called R process peaks. So this is called first R process peak, this is second R process peak, this is third R process peak. So our goal for most of the work has been to actually model outflows like the sun or some magnetized star and see if we can get these peaks around A equals 80 to 90, 130 and 190. If we can reproduce these, means our model is working. And then there are ultra metal poor stars, which look different from solar abundance. So solar abundance is this solid line. Ultra metal poor stars are these circular data points. So this abundance looks somewhat different from the left panel, but we also try to explain this because this is one extreme and that is one extreme. So our results has to explain both, and that's our main goal. So again, coming back to the question, where can our process happen? Firstly, there has to be enough number of neutrons. There has to be a lot of neutrons because first step is seed nuclei capturing neutrons. So there has to be a lot of neutrons. Then neutron capture has to proceed rapidly. It cannot be slow because we saw for S process, there's only one neutron capture event in 10 to 100 years. And if we were to go by slow process, up to 13.8 billion years, which is the present age of the universe, we wouldn't have elements which is like gold or platinum or heavier, mass number 100, 150, 200. We wouldn't see actinides, lanthanides. So we know it has to go rapidly. And then the medium has to be hot and dense. So hot medium is actually helping towards nucleosynthesis. Also, dense medium is helping towards more interaction. If the medium is rarer, then there's less probability for seed nuclei and neutrons to come together. If it's more dense, then there's more encounter probability. So by looking at that, there are three kind of events which one can study. One is core collapse supernova, which is the primary focus of my talk. And then there's binary neutron star mergers. Both of these are neutron stars. And then there can be one neutron star, the other can be black hole neutron star mergers. So we do see gravitational waves from these two events. Not from BHNS yet, but we have seen gravitational wave from BNS. So we know that these exist in nature. We do not know how much nucleosynthesis happens there. So that is the question we try to answer in our work. So I go to core collapse. I focus on core collapse first. So we look at the mechanism for core collapse. So what happens is first there's a star which is about 8 solar mass. It can be 8, 10 solar mass in that range. So what happens is iron is fused in the core of that progenitor, and as iron is fused, uh, the nuclear fuel is used up gradually. So the radiation pressure is decreasing over time, but the degeneracy pressure dominates. So what happens is the stellar core collapses on itself. The core is not 8 solar mass; it's about 1.4 solar mass. So once the core collapses, it's about a 1.4 solar mass star in the center, and it becomes neutron degenerate because it's so dense. And after this collapse happens, there's a supernova shock which is powered outward. So you see these yellow regions, this arrow outward. So all of this material is ejected outward, and in the end, we are left with something like this. It's either a neutron star, so all of this yellow region has been pushed out. You either have a neutron star, which can give out neutrinos, and if there's a black hole, there's no neutrinos because black hole does not give out any radiation. So this is the entire evolution process for core collapse. Uh, our goal is to actually model not just that, but how nucleosynthesis happens in this outflow. So this figure is showing you, this is the protoneutron star, Protomagnetar, where the core collapse is happening. So this is the radius axis about 10 kilometers to 10 to the 5 kilometers, and this is the mass axis. So this is telling you how close to the protomagnetar nuclei are forming. So as you see, neutrons and protons are formed in about 10 to 100 kilometers. So this is a circle, so you can extend the radius from here to there. And then alpha and neutron particles are formed around 100 or slightly more. Beryllium, carbon are formed around 1000. And then heavier nuclei like nickel, silicon, helium, oxygen are formed even outwards. So as the outflow is going further from the protoneutron star, more and more R-process nucleosynthesis is occurring, and we get heavier and heavier nuclei towards the end. Our picture is something like this, what we modeled from our analytical model and also with the simulation. This is the protoneutron star, which is here PNS, the gray area. With a radius r, there's opening angle theta. It rotates, so there's an omega axis, this one, and there's a magnetic field axis, which is at offset. There's an angle which is chi between the two, and these are the magnetic field lines. So m dot is the mass flow rate, so how fast mass is going out from the star in these outflows. And that depends on, these are three factors which depend on F open, F centrifugal, they depend on the magnetic field rotation of the star. And the important factors here are the luminosity neutrinos, the energy neutrinos, the radius of the star, and the mass of the star. We take these quantities from Metzger 2011 model, who gave this for non-rotating protomagnetar, so omega equals 0, but we use some modification to their quantities to actually model rotating neutron stars. So you use eta of 3 and model L mu, E mu, and the time. So the question is, what happens once we model the protomagnetar? What properties do we see? So the first property that we see is sigma 0, which is the magnetization of the outflow. So notice this is phi b, which is the magnetic flux. Phi b is b times r square. So magnetic flux times omega square, rotation period square, divided by m dot. So magnetization of the outflow tells us how magnetized basically the outflow is, in other words. So you would see we are varying the magnetic field from about 10 to the 14 to 10 to the 16. We are varying the rotation period from 1 to 5 milliseconds, and magnetization is highest in this parameter space, which is 3 times 10 to the 16, largest magnetic field and somewhat intermediate rotation. And then there's another quantity which is called the energy loss rate, which is also similar to neutrinos. Sorry, the luminosities. So this is energy over time. We want to know where the luminosity is the largest. So the red color is where the luminosity is 10 to the 50 or larger. You see most of the red is concentrated here. And it makes sense because larger magnetic field means more energy in magnetic field, and faster rotation, P is 2 pi over omega. So if P is small, means omega is large. So most of the outflows here would be very energetic. That means the luminosity would be larger. And then the question is, how do those parameters sigma 0 and E dot influence nucleosynthesis? So for that, we will need to look at the entropy of the outflow and the expansion time scale. So we see the entropy in blue is not really changing much. It's starting from around 10 and it's going to maybe 30 or 40. So it's roughly constant. The expansion time scale is starting from about a 60 and then it increases to maybe 10 to the 4, 2 times 10 to the 4. So this is for magnetized outflows. And one advantage that magnetized outflows have over thermal outflows, which have no magnetic field almost, is that the entropy is lower and the expansion time scale is slower in magnetized outflows, which means nuclei are moving out, but they are not moving out as fast. That means they have more opportunity to synthesize heavier and heavier nuclei because they have more opportunity to interact with neutrons in the outflow. So magnetized outflows have more chance to synthesize heavy nuclei. So that's one thing we established. And then we want to actually know if nucleosynthesis has to happen even. Initially, the nuclei have to be disintegrated because whatever is in the stellar medium, it can be carbon, oxygen, beryllium. Initially, all those nuclei have to be disintegrated to neutrons because unless there are neutrons, there's nothing to interact with the seed nuclei. So there are two processes which do that. One is photodisintegration, the other is spallation. So in this figure, I'm showing the optical depth for both. This is the optical depth for photodisintegration. This is for spallation. Dashed line is spallation. So as you will see, both of them are much larger than one. Much larger than one means the interaction is so strong that nothing survives. So all the nuclei which are loaded into the jet are disintegrated into neutrons because of these two processes. And then they participate in nucleosynthesis. And this is one of our main results. XH is the mass fraction of nuclei which are heavier than iron. So mass number 56 or more. So if you see XH equals 1, it means all the nuclei that are synthesized are heavier than iron. If you're seeing XH of 0.65, then it means 65% of the nuclei are heavier than iron, 35% are mass number 56 or less. So in this case, you see that as YE is smaller, there's more nucleosynthesis because XH is larger. So zero point 0.4 gives more nucleosynthesis compared to 0.5, which gives more nucleosynthesis compared to 0.6. So YE has an inverse correlation with the amount of heavy nuclei that is synthesized. But this is using this analytical expression here, which is from a 2012-2014 paper. And I will show later that there is some error to this expression. So we try to correct that error, and for that we need to use our own code, a different code, which actually corrects this prediction. So this blue line is overestimated. We will see later. Also, this not just a 0.4 line, also the 0.5 line is overestimated. So these corrections have to be done, but it's difficult to do them analytically. We need to use a code which actually has all the reactions and isotopes. So everything can be accounted for, and that cannot be done analytically. So this is the contour plot for XH. So again, in the magnetic field and rotation period space, more red means more nucleosynthesis. So here you will see that more red is focused in this region. So it's telling us that slightly smaller field, maybe 10 to the 15 or less, but rapid rotation is giving us more nucleosynthesis. And these are at two different times. So this is the breakout time. Breakout time is the time when the jet is actually coming out of the stellar ejecta. So there's an outflow, which is moving within the star, and there's a time when it's breaking out of the star. So that's the breakout time. It's about 10-15 seconds. And this is the time when the medium is thin to neutrinos. So the time when neutrinos can propagate out of the stellar medium. And this time is about 70-80 seconds. So as you will see, even though we move from 10-15 seconds to 70-80 seconds, this pattern is not changing majorly. You still see most of the red here and most of the blue here. So this parameter space is not ideal for nucleosynthesis, and this is the most promising. But again, there are corrections to this because this is what we are getting from the analytical expression, and it's not exactly true. So we move to Skynet, which is the code that we use. What Skynet does is it takes some input parameters and their density, temperature, electron fraction of the outflow. And then what it does is it has about 8,000 nuclei. So the periodic table has about 230 to 50 nuclei, but there are many different isotopes. So we add all those isotopes, we get about 8,000, and there are all these reactions, 100,000 reactions, which are included within the code. So it tells us, for example, if let's say cesium has to decay, what's the dominant reaction, and then what are the 2, 3, 4 other reactions through which cesium can decay, but they are not producing, their rates are not as high. So you have 10, 100 reactions for each nuclei, but not everything has the same rate. One of them is the dominant channel, then the others are subdominant to that, but it includes all the reactions together. And then this helps us to make precise predictions for elemental abundance, not like what we had earlier for XH, but now I will show we get these abundance, which we actually see is close to what we see in stars. So once we feed these density, temperature, and electron fraction into Skynet, uh, and we vary the time. So this panel is 4 different times. T start is 0.5 seconds. This is the breakout time, which is about 10 seconds. Then this is photo disintegration time, which is about 40-50 seconds. And this is the time when the energy of the nuclei is the maximum after acceleration. This is about 70-80 seconds. So you will see as the time increases, on average, there is more nucleosynthesis. So the curve is moving towards the right. There is one exception. Red is actually moving to the left instead of green. But on average, you will see that this peak is happening towards the right. So green has peak around 110, then orange had peak around maybe 90, and blue had peak around maybe 70. So more time helps nucleosynthesis as we saw earlier. And then if we fix the time, and if we just vary the electron fraction, then we see what we saw earlier. Smaller YE actually gives us more heavy nuclei. So you see this tail is slightly longer, extending up to 90 for 0.45, but for 0.55, this is only going up to 60, 65. So smaller YE is helping and more time is helping in nucleosynthesis. Then the next thing that we did is actually we did the same contour plot, but in mass number. So what is the average mass number in the BNP space is the question we asked. And as you see, the average mass number at most is about 35 or 40. So even here, where it's most red, we see that the heaviest nuclei that we can get is still lighter than iron. Iron is about 56, but this is 40. So maybe calcium. It doesn't go much beyond that. So higher magnetic field, which is here, and smaller spin, which is here, is helping nucleosynthesis. But still, we find in core collapse, we do not find nuclei which are heavier than mass number 40. Whereas in the periodic table, we know it extends up to 230 to 50. So the question still remains, what is generating nuclei from 40 to 250? If it's not core collapse, then what other process is responsible for that? Uh, Before we answer that question, I'll actually go over the acceleration of the nuclei and survival. So there are two plots here. The first plot here, so there are two axes. It's slightly confusing, but the left axis is the maximum energy of the nuclei, and the right axis is the optical depth for photodisintegration. So if we want to see the nuclei at Earth, then they should not disintegrate, which means Fa gamma has to be less than 1, so it has to be below this line. Dashed line is the disintegration line. So anything that you see within this white unshaded region has Fa gamma less than 1, which means it is surviving, it's not disintegrating, and also it has energy which is larger than 10 to the 20 eV. So why is 10 to the 20 important? Because it's the cosmic ray energy. So this is the allowed parameter space or the allowed time from 20 seconds to 55 seconds, where nuclei can be accelerated to cosmic ray energies, and also they are not disintegrating, they are surviving, which means we can see them on Earth. So it means that although the outflow is traveling for a long time, it starts from about 0 seconds before 10 seconds and it continues up to 100, 200 seconds. But there's only a very small window where we can see cosmic rays because only this parameter space is allowing the energy and optical depth. And about survival, this plot is about survival. It includes 4 different processes. I wouldn't go into the details of these, but GDR is basically photo disintegration. G4 and fragmentation are different processes. As you see, GDR is the dominant process. So this is T to the minus 1, which means it shows which process is dominating in disintegrating the nuclei. And because black curve is the highest, it means photo disintegration through GDR is the dominant process in disintegrating the nuclei. But as we see in this region, even though photodisintegration is dominant, still the nuclei can survive because Fa gamma can be less than 1. Then wrapping up, summarizing a bit, core collapse as source of ultra high energy cosmic rays. We saw that they can accelerate nuclei up to energies as high as 10 to the 21. The low entropy and expansion time scales in these outflows are helping in the production of first peak and a little bit of second peak R process nuclei, but not more than maybe mass number 90, 100, 120. So we still need to know what gives us second and third R process peaks and actinides. So if it's coming from other astrophysical sources, what sources are those? So they can be mergers, neutron stars, or black hole mergers. Can they give us the third R process peak elements? We need to answer that question. That is in the next slides coming up. So again, coming back to the part where can our processes happen, we have looked at core collapse supernova, which is this one, but now we'll be focusing on these two, which is BNS merger and BHNS merger. Now we will get the nucleosynthesis yields from these two and compare it with CCNE and see if this can give us second and third R process peak, because this is only giving us first R process peak and it is not enough. So this is a brief schematic of how a black hole neutron star merger ejecta would look like. So there are many different things which are going on here. One is a jet in blue, which is going out. Then there's a cocoon in orange, which is surrounding the jet. And there's an accretion disk in purple. And there's a dynamical ejecta in yellow. So we do not need to look at all these components. We only need to look at the components where nucleosynthesis can happen. And there are only two components where nucleosynthesis happens. One is the dynamical ejecta and the wind. So from here on, I'll focus on these two and show the results for only those. So this is showing the nucleosynthesis abundance pattern in binary neutron star and black hole neutron star mergers within the dynamical ejecta. So you see that there is a peak here around A equals 120, which is the second R process peak. There's a peak around 60 or maybe slightly more, the first R process peak. Then there's a peak around 190, which is the third R process peak. So from mergers, these two types of mergers, we are getting first, second, third R process peaks plus actinides, which is this. Whereas if we were to just look at wind or core collapse, what we were looking at, we were looking at this green curve until now. It was completing at 90 or 95. It was not going above 100. So when we added magnetized core collapse case, this green curve is becoming blue and it's extending up to 130. And if we have merger, then this red and black curve is also extending up to 130, 140. So we find that neutrino or thermal core collapse supernova is mostly first R process peak, but magnetorotational or merger is second R process peak or even higher. So this is more promising. This is answering our question that where is second and third R process nuclei are coming from? They are coming mostly from mergers, not core collapse. Now again, looking at this periodic table, we haven't modified this, but we are in the process of modifying this. Now we know how much fraction is coming from neutron star mergers. We can add black hole neutron star mergers to that. And with type 1a supernovae or core collapse supernovae, we can add magnetorotational supernovae. So we can now modify this periodic table completely and all these colors will change. And this 2020 table, we will get a new version of this now in 2022, 2023. And that was our goal as to how much this periodic table has changed since 2020 with our analysis. That is one result that we will produce. We are still working on that, but that was one of our goals when we started this work. And now I'm moving to propagation in outflows. So these outflows are moving in stellar medium, which is shown in blue here, and the outflow is shown in yellow here. So we consider three different types of outflows. One is a Wolf-Rayet star, which is this one. So it has a smaller radius. It has a radius of about few times 10 to the 11. And then there's blue supergiant and red supergiant, which has radius of few times 10 to the 12 blue, and the red supergiant has few times 10 to the 13. Uh, so we want to see if there's an outflow here in yellow, whether it becomes collimated or not. So if the outflow is collimated, what happens is it starts like this as a conical shape, but then it becomes cylindrical. The neutrinos are coming from here, but if it's not collimated, then it continues and moves out of the cocoon, which is this orange region, like a conical shape. So there's more area for the neutrinos to come out, and also there's more area for the nuclei to propagate because they're propagating in conical volume instead of cylindrical volume. So when we are looking at those outflows, one question we want to answer is how much energy is the jet depositing into the cocoon? So you see this jet is traveling into the inside the cocoon. So this yellow region jet is traveling inside the orange cocoon. The question we want to answer is how much energy is going from the jet into the cocoon. That tells us how much energy is left with the jet when the jet is breaking out of the star, out of the blue region finally. So we model this for all three progenitors, WR, BSC, RSC. This is the energy which goes into the jet, and pressure is energy by volume. So here we are showing contour plots for energy. This is for volt-fried, blue supergiant, red supergiant. As you will see for volt-fried, the maximum energy, the patterns are looking somewhat the same. But the maximum energy in volt-fried is 10 to the 49 arc. For blue supergiant, it's about 10 to the 50. For red supergiant, it's about 10 to the 51. So most energy is deposited for red supergiant. One reason is also because the breakout time for red supergiants is 2000 seconds, whereas for volt-frieds it's about 10 to 15. For blue supergiants it's about 100. So there's just more time for the jet to put energy into the cocoon. This has 2000 seconds, so this can put 100 times more energy than you can put in about 10 seconds. That's what is happening. This is about 100. This can put 10 times more energy than volt-fried. So that is one thing, how much energy is going into the cocoon. The next thing is if the jet gets choked inside the medium or not. So whether the jet stops inside this blue region or this actually breaks out of the blue region is the next question. So this is determined using the integral that I show here. So the integral on the left, E dot J iso time integral, this is basically the jet luminosity integrated from the start to the breakout time. So if this quantity is larger than the energy in the cocoon, then the jet has enough energy to break out of the cocoon. So we take this ratio, we take the integral of Ej iso, we call it E tilde J iso, and we divide it by E ejecta. And wherever this ratio is more than 1, means the jet has enough energy to break out of the cocoon. It doesn't get choked within the medium. We see that it is almost always greater than 1. This is 1, so it's blue or higher for blue supergiant and 10 or higher for red supergiant. So both of these do not have any configuration where the jet gets choked. But for blue supergiant, there's a very small region, this one, where the jet can get choked. So for most of our configurations, for most of our outflows, the jet is successfully breaking out of the ejector. The jet is putting enough energy into the cocoon, but even after putting that energy, the jet has enough energy left so that it breaks out of the star. And the last thing that we want to look at is whether neutrinos can be produced in these magnetized outflows. So because these are magnetized outflows, we know that a large part, the dominant fraction should actually go into magnetic energy, not the kinetic energy of the outflow. So the dissipation that happens through magnetic dissipation in these outflows. And then once magnetic dissipation happens, particles are accelerated, particle kinetic energy is increasing, so their temperature is increasing. So for larger particle temperature, the nuclei are dissociated into neutrons and protons again. So they start from neutrons and protons, they become heavy nuclei, but if the temperature becomes large, they are again disintegrated to protons and neutrons. And then these protons are interacting with photons in the jet, so that yellow region, and they give rise to what we call pions. And these photons are mostly thermalized because the optical depth is much larger than 1. And high energy neutrinos can be produced through proton-pion interaction, or rather photopion interaction. These pions can interact with photons, and then they can generate neutrinos which can travel up to the Earth. So this is the neutrino line, and this is the photon line. So we see the photon through GRBs. The question is, do we see the gray line, which is neutrinos? Because if we see both, then we know they have a common origin, and then it becomes much more easier for us to constrain the star or the source. So this figure is showing the flux in neutrinos. The x-axis is the flux computed up to the radius r star, and as you will see, the flux is the largest for for red supergiants. The red curve peaks around 10 to the 7 GeV. GeV is 10 to the 9 eV, so it is very high energy. Blue supergiant is peaking around 10 to the 5 GeV, and then the Wolfrat is peaking around 10 to the 3 GeV. So the least energy is in the Wolfrat progenitor. The most energy is in the red supergiant progenitor. There's a spectral break which is happening here below the peak. This for red, that for blue, and this for green. The spectral break happens at the highest energy for red supergiant as compared to blue supergiant as compared to Wolfrat, because this is directly proportional to the jet Lorentz factor, and the jet Lorentz factor is the highest for red, then blue, then green. And then above the peak, there's exponential suppression, which you see is largest for red, intermediate for blue, then slightly slower for green, which is Wolfrat. So from the flux, we can get fluence. So fluence is time integral of the flux. You take the flux, you do dt integral 0 to t breakout. That gives you fluence. And fluence is again the highest for blue supergiants. It's again peaking around 10 to the 7. It is significantly smaller, around 10 to the 4 for, sorry, this is red supergiants, significantly smaller for blue supergiants. For Wolfrats, it's barely visible here. The green curves, few times 10 to the 3 to 10 to the 4. So for Wolfrats, which is the green curve, neutrinos for with energy which is 1 TeV or larger, 1 TeV is 10 to the 3 GeV or larger, are very scarce. They are very less in number because there's strong inverse component cooling, and also there's attenuation at early times. So this fluence is very small for detectable signal. It's very hard to detect. For blue supergiants, which is for supergiants, which is either the blue or the red curve, we can see neutrino spectra up to PeV energies. PeV is 10 to the 6 GeV. So we can see that, and because we can see peaks around 10 to the 6 GeV, these neutrinos can be detected for both BSG and RSG scenario. So we compute the number of neutrinos which can be detected from these events, and that is given by this integral. There's the effective area of the detector, then there's the fluence, which is shown in this curve. So we take the y-axis, we multiply it with area, and we multiply it with the energy, and we integrate it from this range. We start from 10 to the 3 GeV, we integrate it up to 10 to the 8 GeV, and we see what number we get in the end. And that number is shown in this table. So we have a source which is fixed at 100 megaparsec. We assume a fixed source distance, and then we say that for different B and P configurations, Wolfrat versus blue supergiant versus red supergiant, how many neutrino events we get every year. So for Wolfrat, you see that this number is 0.1 or less for even the most optimistic configuration. So from Wolfrat, we almost do not see anything. It's 0.1 event per year, which means one event per 10 years. So it's very hard to detect. For blue supergiants, we see about 10 events per year. For red supergiants, we see about 50 events per year. So this is the most promising for seeing neutrinos. This is intermediate and somewhat promising. This is not at all promising, Wolfrat, for finding neutrinos. So I think this kind of, yeah, this just concludes in the sense that BSGs and RSGs are detectable, Wolfrats are not really detectable with neutrinos. And then this is the place where I try to summarize the main results from this talk. So the first result is about nucleosynthesis. So first question we asked is, can we synthesize nuclei that are heavier than iron? in magnetized outflows from protomagnetars or not. And we found that yes, we can synthesize some nuclei, maybe mass number 30, 40, 60 iron or slightly heavier than iron, but we cannot synthesize more than that. So we found that rapid rotation and strong magnetic field helps in nucleosynthesis, but we still found that we cannot go beyond A equals 60 just with core collapse. Then we looked at the condition when the nuclei can survive and also get accelerated to ultra high energy cosmic rays. And we found that there's an intermediate time window, 20 to 50 seconds, when the nuclei can survive and they're also accelerated up to high enough energies so that they become cosmic rays. And coming back to our process, we concluded that core collapse is the main contributor to weak R process. Weak R process means first R process peak or less, 60 or less. Whereas binary neutron star or black hole neutron star mergers are more likely to synthesize second and third R process peaks, which is A equals 130, A equals 190, and actinides, which is 200 or more. And then relativistic jets from the protomagnetars, we looked at propagation and we saw that they are staying uncollimated. So they start conical shape and they break out as conical shape. They are not becoming cylindrical. They break out of their ejecta successfully and they're also stable. So these jets have magnetorotational instabilities, but those instabilities do not break the jet. They are staying stable until the time of breakout. And lastly, we looked at neutrinos of very high energy, 1 TeV or more. This is 10 to the 12 eV or more. And we found that we can get neutrinos, but not from all sources. We can only get them from blue supergiants or red supergiants. From Wolf-Rads, the case is kind of hopeless. We do not really see many neutrinos for those. And this is at a distance of 100 megaparsec. If we were to increase the distance, then we would see fewer neutrinos because it scales as 1 over d square, the number of neutrinos. So we fixed at 100. If we change it to 50, then we will see 4 times more neutrinos. If we change it to 200, then we will see 4 times less neutrinos, and so on. So this essentially wraps up the picture. First is nucleosynthesis, then there's acceleration, then there's propagation, and this is about neutrinos. So our goal is to integrate all of this together and see if core collapse versus BNS merger versus BHNS merger can explain cosmic rays, neutrinos, and also gamma ray burst. I haven't really talked about gamma ray emission here, but this is one component which can also be looked at. And then there's also gravitational waves from these events. So gravitational waves is another signal. So if we can integrate all 4 into one picture, that's our end goal. And it means if we see one gravitational wave event, then that detector can send an alert, and then we can start following up for gamma rays. And once we see gamma rays, we can observe cosmic rays, and then we can observe neutrinos. If we can see 1 out of 4 or 2 out of 4, it would be the best detection that we can get. But that is still about 5-10 years away from us in terms of technology. So hopefully we will get there by end of this decade, 2030 or so, as our detectors are improving. But at this point, we have the theoretical model ready. In case we get a detection, we know what parameters to put into our code and generate results so that we can compare with observations. So with this, I'd like to thank all of you for your attention, and I would be happy to take any questions. Yeah.
You talked about the magnetic.
Magnetized core collapse supernova. Yeah.
So there are many objects which are not magnetic at all.
Mm.
Will this applicable to those objects also?
Yeah, so we have looked at like 4 different cases. One is non-magnetized core collapse supernova. One is magnetized core collapse supernova. So remember this blue event here is non-magnetized. It's just core collapse with neutrino-driven outflow. So this also we can model in the limit that magnetic field is very weak. It's not 10 to the 14, 10 to the 16, but maybe 10 to the 6, 10 to the 8 Gauss. But then we make the magnetic field stronger in our system and say as the magnetic field is tuned up, how is the nucleosynthesis affected? So we already know the results from the non-magnetic outflows. Our goal was to introduce magnetic field and see how the abundance yield of different element is pushed up or pushed down, and we found that it's pushed up. So most of this blue region is contributed from non-magnetized, but our prediction is when we add magnetic field to this periodic table, the magnetized core collapse supernova contribution will be at least this blue or larger. So when we renormalize, when we add that contribution, then this blue will become smaller. And then let's say we add another color, yellow. So that would be magnetized core collapse. That would be slightly larger than normal core collapse.
And if you add this GRB,
Hmm.
how the figure will change?
So this is mostly just from the cosmic rays. Cosmic ray, because cosmic ray is giving us the composition. So if we add GRB, then that wouldn't really give us information related to the abundance. It would tell us mostly what energy we have. So it can tell us maybe 10 to the 20, 10 to the 21 EV nuclei or not, but it would not tell us if it's iron nuclei or silver nuclei or cesium nuclei. So this information is coming entirely from cosmic rays, not GRBs.
Even in case of the GRB,
Hmm.
you light curve pattern also sometimes how they fall.
Yeah.
That also gives some indication
About the composition?
Yeah.
Yes, but it will tell us like what fraction is in. So
Yeah.
it cannot tell like individual elements, but maybe lighter than carbon, heavier than carbon,
Yes,
like that.
yeah, like
Yeah.
that. Yes.
Yeah, yeah.
Rough case.
Yes.
Okay.
Micro-updated NMN object.
Yeah. For white dwarfs, we didn't really run our codes, but there are other groups which have done. They didn't really get nucleosynthesis beyond, I would say, the second or the third row. So most of whatever goes after third row, like fourth, fifth, sixth row here, has to involve neutron star events, either mergers or co-collapse.
One
Yeah.
yes. So, is there any chance if we say replace the nucleus and black hole from the Bhattacharya module, event horizon, some
Yeah.
contribution is contained from the
Okay, so yeah, that is one thing we did in this work itself. So as you see in this figure, right, this is for BHNS merger. So there is this accretion disk and dynamical ejector. For BNS merger, this this disk and dynamical ejector, the disk is not really as much there for BNS merger. The dynamical ejector in this case is focused in the equatorial plane. For BNS merger, it's more isotropic. So we can get the abundance pattern for BNS versus BHNS, this red versus black. And we see that the black is giving slightly higher abundance, around 100 to 200. And below a certain number, like here, also black is dominating slightly. So BHNS gives slightly more abundance from 10 to maybe 80, 90, then again 100 to 180 or so. But here it's like BNS is higher, like maybe 4 or less. BNS is higher, but for most of the A, 0 to 200, BNS is giving marginally high heavy nuclei as compared to BNS. So, and also here, the black is again BHNS and the red is BNS. So as you see, the black is higher than the red, around 100 to 140. This is the wind, and that is the dynamical ejector. So these are two different components. Wind is this one, what is coming out of the disk. Dynamical ejector is what is coming out of this yellow uh, half circle. Kind of. Yeah.
anybody who would have question? Thanks again, speaker.
Thank you.
We have some tea outside.
Okay, here only.